All right, here we'll do the second part of problem 103. Last time we figured out the reaction forces at C and A. So just to put that in here, we know that the reaction force at C, we know the direction it acts because it's a 2-point element. That is 9.24 kip. It's positive, so it's acting in tension. The X component here is actually minus 4.67 kip, so it's actually acting in compression. And then the Y component at A is going to be 8 kip. So I guess on all these, I just always kind of do the disclaimer. There may be some errors, so you should always think about what I'm doing, check my work. I always make arithmetic errors. I'm really bad at that. And the other one is, I think the best way to use these videos is to try and solve the problem first yourself. If you get through it, great. Or if you get through it and you're unsure whether you did it correct, you can look at the video. Or if you get stuck, look at the video and see why you got stuck. I think it's a much better learning experience than just watching the movie and eating some popcorn, okay? So try to do the problems first. I probably should have stated that earlier. Maybe I'll post that on the blackboard, okay? All right, so first let's look at sizing BC. So I know in BC this dimension here is given at 1.5 inches. And I also know the maximum allowable stress in element BC is 29 KSI, okay? 29, what am I writing to? 29 KSI, okay? So that's the maximum allowable average normal stress, all right? Tension, compression, obviously. In this case, we already know that it's acting at tension, all right? So we can figure out that, all right? That one gives me if we look at element BC, it could have a normal, a shear, and then a moment. But you can look at this and you can see, obviously, since it is a two-element member, that the shear and the moments are going to go to zero, right? That's what makes it a two-point force element. And the only non-zero component is going to be the normal, and it's in tension, so this equals the 9.24 kip. All right, and again, if you don't see that, do the sum of forces, sum of moments as an exercise, but I think by now we should be all pretty comfortable with doing those. All right, so the average normal stress has to equal that max, or this is the limiting case. I guess technically I should say less than or equal to. But the limiting case is where it's equal sigma max, and that equals N over the area. So the area is the thickness times 1.5 inches. And we know this force is the 9.24 kips, and we know this value here is the 29 KSI. So we can solve for T. T equals 29 KSI times 1.5 inches divided by 9.24 thousand pounds. So the K's cancel out, the pounds cancel with the pounds, the inch here will cancel with the inch squared here, and this will give me units of inches. And then if we just do the math correctly, 29, enter, 1.5 times, divide by 9.24, and that gives me 4.71 inches. Seems kind of thick now that I'm thinking about it. I wonder if I did that right. I'm just looking at the, if this is 1.5, and the pictures in the book, it looks like this would be a bit high if it's drawn to scale. But maybe that's it. This is the area. That is the force. That's the max allowable. So, oh, yeah, it is wrong. I'm sorry. These two had to be switched. It's T equals, let me do it a little more slowly. I apologize for that. T equals N over the 1.5 inches over the sigma max. I put the sigma max on top. This is the 29 KSI. This is the 9.24 kip. And I was even sloppy. I didn't even catch myself in inches, so I should have been able to do that. All right. Actually, yeah, this would have been 1 over inches. Okay, so that'll come up better. It's the same thing, just the inverse of that, okay? So you can plug through the numbers. 9.24 kip over 1.5 inches times 29 KSI. All right. So pounds, the pounds will cancel out, the K's cancel out. Inch squared, so this is a 1 over inch, which puts inch in the numerator. So that's 1 over 4.71 inches, okay? Which is 0.21 inches, okay? Which looks a little more to scale, okay? So that's the thickness of element BC. All right? Okay. Why don't we stop there? I know it's been short, but then we'll do the shear next. Okay, so we'll consider the shear failure for the pins at points A and B. All right?